Welcome everyone. In this video lecture I will explain how to determine the natural frequencies and modes of vibrating strings. I have sketched here a vibrating string that is fixed on both ends, so at axis 0 and axis L, and the equation of motion in its homogeneous form as we derived in last lecture, as well as the string's boundary conditions. So for determining the natural frequencies and modes, we can consider the homogeneous equation of motion, since the frequencies and modes do not depend on the external loading. So let me first start by deriving the general solution for free vibrations of these equations of motion. For that, I'm going to use a method called separation of variables. Separation of variables. And this is a method, I believe, that was introduced by Mr. Fourier. The idea behind this method is that we take the displacement field, v, which is a function of x and t, and we try to solve this by splitting it, in a multiplication of a function that I will call capital V, which is only a function of x, times a function capital F, which is only a function of time. So basically this is a particular trial solution, and we will substitute it into the equation of motion and see if it works. So by taking the second time derivative, we just keep v and differentiate f twice, and for determining the second spatial derivative, we differentiate v twice and keep f. So the result will be, once we substitute this into the equation of motion, rho a times capital V times f double dot, where I will use a dot for differentiation with respect to time, minus t times v double prime, where I will use a prime for differentiation with respect to x, times f. And this should be equal to 0. Now the method is called separation of variables because I will put everything that contains f on the left hand side and the rest on the right. So the result will be that I can write this by dividing the entire equation by f as 1 divided by f times f double dot. And then on the other side of the equation we have t divided by rho a times 1 divided by v times v double prime. So basically all the time variables are on the left, all the spatial variables are on the right, and there's also this constant still involved. So how can this be true? How can a function of time be equal to a function in space? In general, this cannot be the case unless both sides of the equations are equal to a constant. So these must be equal to a constant. Let's call it c. And this is called the separation constant. Separation constant. So we can work with this constant c, but since I already know what the result will be, I will redefine this constant to be minus omega squared. And once you see the result, you will understand why I do it like this. So if I now focus on the time part of the equation only, I'll multiply both sides of the equation by f and take everything to the left. And then we have f double dot plus omega squared times f is equal to 0. Well, this is now an ordinary differential equation in time, of which the solution is very familiar to us because it's what we have obtained in analysis of Estov systems before. So the solution is simply a sine-cosine combination where the argument is omega t. So the solution can be written as cosine omega t and then a function with sine omega t. So from this, I think it's clear why I choose this separation constant to be minus omega squared, as the behavior in time indeed describes vibrations. These are harmonic functions in time. All right, Now let's also see what the result will be in space. So for that I will multiply both sides of the equation by v, rewrite it slightly as follows. I will do the second derivative of v, and then we will have plus rho a omega squared divided by t times v itself is equal to 0. Now also this is a second order ordinary differential equation, but now for the variable x. But the general solution is very similar, and I can write it as a sine-cosine combination now in terms of x, and the argument should be the square root of this times x. So in order to write this down in a more compact form, let me introduce beta, let me define it as the square root of rho a omega squared divided by t, like this, such that I can write this solution, the general solution, as the cosine of beta x plus c2 times the sine of beta x. So we see that the behavior is harmonic in time, but also the shapes of the string, as I have already sketched a little bit in this figure above, can in general be described in terms of a cosine and a sine, where this beta is basically the equivalent of what a frequency is in time, and it's sometimes called the wave number. So basically it is something that describes how many oscillations there are in a certain length of string. So the general solution is a combination of this v and f. Let's now see what the natural frequencies are. For that I'm going to apply the boundary conditions on v. So let's first start by rewriting these boundary conditions using separations of variables. So v at 0, time can be written as capital V at 0 times f for all times. And this should be equal to 0 at all times, because on this point the string is fixed, which means that I can just cancel f, since this f is not 0 at all times. And very similarly, v at L and t can be written as capital V at L times f of t. And since this should be 0, and since f is not 0 for all times, v at L should be 0. So let's use these boundary conditions onto the general solution for v as a function of x. And let's see what happens. So when we demand that v at 0 should be 0, we substitute it and conclude that c1 must be 0. Hence, there are no cosines in this shape of string. And then finally, when we have v at L equal to 0, so c1 is already 0, so we have that this should be c2 times the sine of beta L. Okay, there are two possible ways for this to be true. The first possibility is that the c2 is 0 as well, but that would mean that both c1 and c2 are 0, and simply that v as a function of x is 0. Okay, this means that no deformations can be described whatsoever. So this is not very interesting. Then the string would be just at rest. So the only other option is that non-trivial solutions are obtained only if the sine of beta L is equal to 0. Okay, now this is called the characteristic equation. Characteristic equation. And it's really the equivalent of a characteristic equation that we encountered for discrete systems. However, in this case, there are infinitely many solutions for this to be true, because let me denote these solutions by beta n. This characteristic equation is satisfied whenever beta n times L is equal to an integer number, an integer multiple of pi, where in this case n start counting at 1, because for n is 0, the sign of 0 is 0, and then we still have this 0 solution again. So this is the solution of the characteristic equation, and now we are very close to finding natural frequencies, because if we now back substitute this into the relation for beta that I have boxed here in the right upper corner, then we can conclude that beta n squared is equal to n squared pi squared divided by L squared. And this is equal to rho a omega n squared divided by t. And from this I can solve for omega n. So omega n equals, let me write it down like this, n times pi times the square root of t divided by rho a L squared. And this is then for n is 1, 2, and so on. So these are the natural frequencies of the vibrating string. We see that they are linearly spaced like this. And so remember that we get to these natural frequencies by applying the boundary condition on the general solution, natural frequencies. And there are infinitely many natural frequencies. Okay, now how to determine the corresponding natural modes? Well, for that I will recall that the sign of beta L is equal to 0 for specific values of beta. Okay, so that means that only at these values it's true. And from the fact that C1 is 0, we already know that the cosines are not in the solution. So as a consequence, let me say capital V n as a function of x can be some arbitrary scaling coefficient that I will call alpha again. And then there can be only signs with a specific argument that solves the characteristic equation. So in this case, these are values for beta that are n pi divided by L. So I get n pi x divided by L. And then also for n is 1, 2, and so on. So these are the natural modes corresponding to the natural frequency. Yeah, so we use these functions for which the characteristic equation is satisfied. Natural modes. And we see that they are also infinitely many, and there are signs only. So let me try to sketch this maybe. Let's see how my drawing skills are today. So if this is the string, then the first natural mode looks like this. It is just half a sign. Okay, so that is for n is 1. Now for, let me maybe do it like this. So this is for n is 1. For n is 2, we get the sign of 2 pi x. So that means that in length L, there is exactly one full sign. So this is for n is 2. And then for 3, we see that there is 3.5 sine functions. So it's something like this. Yeah, for n is 3. And so on. So you see that the corresponding modes are functions of x that describe how the string is vibrating, if it does so in a natural frequency. And the scaling is still arbitrary. We just know that these are sine functions. Okay, so in summary, for determining natural frequencies and modes, we first establish the general solution in space, capital V, and then apply the boundary conditions to it, and we solve for the characteristic equation. Okay, now with this we can move on to solving free and forced vibrations, and that will be done in the next lectures. Thanks for watching.